Hey everyone, can you hear me? All right. Yeah, I'm Will Doebler from NASA. I'm going to be presenting today on some simulation experiment design and visualization techniques for an X-59 low boom variability study. And I'd like to acknowledge my colleagues Sarah Wilson and Alexandra Lubeau for their stats support and guidance along the way. For the presentation overview here, I'm going to give a brief introduction on sonic boom background info. Then I'll describe the X-59 mission. I'll outline our sonic boom simulation goals, and then we'll show the experiment design approach. Finally, I'll show the simulation results and our visualization techniques. To start off, we have a brief abbreviated history of civilian supersonic flight here. Some of the highlights. In 1947, the sound barrier was first broken by Chuck Yeager, and supersonic aircraft were rapidly developed thereafter. The entire time the supersonic aircraft is flying faster than the speed of sound, it's producing a sonic boom, which can be heard on the ground. And in the meantime, there were sonic boom community tests where these supersonic aircraft were flown over the Oklahoma City area. It was coined Operation Bongo, and during this community test, over 1,200 sonic booms were delivered to this community, up to 8 per day. And members of the communities were regularly asked to report their perception and annoyance of the sonic booms. Of course, many reported some annoyance and disruption. And by 1973, the FAA had finalized a prohibition of civilian supersonic flight over land, in part due to the annoyance induced by the sonic boom noise. But supersonic flight over water routes were still possible, and that's what Concorde did to serve the U.S. market. And despite this prohibition, there will always likely be demand for high-speed transportation, whether it's to get you guys to your cross-country business meetings or your next conference quickly, or to extend the range of organ transplants. There's also been a push to reduce the loudness of sonic booms over the years, and one such advancement was NASA and DARPA's Shaped Sonic Boom Demonstrator program. This program proved that you can change the shape of the aircraft in order to reduce the loudness of the sonic boom. And very recently, the FAA was charged by Congress to reevaluate its supersonic prohibition in light of these aircraft shaping advancements. And the main focus of this talk is going to be on the X-59 aircraft, which NASA is currently having built by Lockheed Martin, and it's designed to have a low loudness sonic boom, and it will be used to collect perceptual data from people in communities across the USA. The data will be provided to the ICAO and the FAA in order to aid in the creation of potential future aircraft noise certification standards. So what's the difference between the shaped sonic boom and a low boom? On the left side here, you can see that there's a traditional aircraft Schlieren image. There's a complicated shock pressure pattern near the aircraft. And as that shock pattern propagates from the aircraft to the ground, the shocks merge together and form this N-wave shape. So here's a pressure versus time cartoon. And the shocks coalesce at the front, and you result in these two loud bangs for the front of the aircraft and the rear of the aircraft. But for a low boom aircraft, which is on the right, this is a Schlieren image from a wind tunnel test. There's much less shocking, much less shock type pressure. You can shape it in such a special way such that the aircraft's shocks don't merge, and instead of two loud bangs at the ground, you get a pair of quiet thumps. This reduces the loudness significantly and will hopefully be quiet enough to be acceptable for civilian overland supersonic transport. Like I said, As the entire time the supersonic aircraft is flying faster than the speed of sound, it's dragging a carpet of sound behind it that can be heard 20 to 50 miles wide, depending on the altitude and the weather of the day. And the flight paths can be, thousands of miles long, so a noise that can be heard 50 miles across over that distance can affect a lot more people than what's traditionally affected by aircraft noise, near aircraft or airports. So the loudness of the X-59 sonic boom and the size of its exposure region are topics of interest for our presentation, and they can change due to the weather of the day. So next we'll talk a little bit more about X-59's mission. The X-59 is currently being built. It's designed to fly at Mach 1.4 and produce a low loudness sonic boom of 75 decibels on a perceived level scale. This is a different decibel scale than you're probably used to, in that it correlates with human perception of impulsive noise. A-weighted decibels and other types of decibel scales typically correlate with continuous noise or noise of much longer duration. So this aircraft will be flown over 4 or 5 communities across the U.S. to collect perceptual data from residents of the communities, and noise monitors will be placed in the test area to record the loudness of the low booms. Members of the communities will respond to surveys reporting their perception of the booms, and the data will be provided to the ICAO and the FAA. So for our purposes, we wanted to know how the X-59 noise exposure region and size, the size and the loudness will change due to the prevailing atmospheric conditions. So we conducted a large-scale simulation study to aid in planning the community flight tests. Next, I'll look at the goals of our sonic boom simulation. We wanted to look at the low boom loudness, its variability, the exposure region size, and the exposure region size's variability. This will aid in the test planning for the X-59 and also make sure that the X-59's low boom would stay quiet in non-standard atmospheres. The X-59 was designed to be quiet in a standard atmosphere, but the standard atmosphere has no winds, and it's sort of an average profile, but may not be representative of a typical atmospheric profile for a day. And our factors of interest driving the variability are the climate, the season, the flight direction, the time of day, our geographical location, ground elevation, and then of course we're always balancing our computational constraints and trying to meet project schedules. So we have our flow diagram here on the right of the simulation. We provide our PC boom acoustic propagation model with the aircraft trajectory information, so that's its Mach number, altitude, and heading. We also have computational fluid dynamics acoustic data near the aircraft that we provide to the model, and then we have our atmospheric model data. It's jumping around on me here. Sorry about that. The outputs of PC boom are the size of the exposure region and the low boom loudness of the X-59 signatures. Finally, I'll show our design of experiments approach for our boom simulation. And because we were unsure of where the X-59 is going to be flying for these community tests, we wanted to get good geographical coverage of the U.S. So what's shown here are 2 different spatial resolutions we were considering based on how much computational time we had. And it was chosen using a fast flexible filling design, which provides, of course, good space filling of the irregular shape of the U.S. All you have to do is provide it linear constraints of your shape and how many points you want, and it'll fill the design space for you. So we were going to look at 2 spatial resolutions of 150 and 450 locations across the U.S. And then we also needed to figure out exactly how much time resolution we needed. So we completed a subset simulation in the Northeast USA, and we compared 34 versus 10 locations and 4 versus 1 atmospheric profile per day over 5 years of atmospheric profiles and 4 aircraft headings. We chose this region in the Northeast because it will have some seasonal variability, and Pennsylvania has been shown in some trade studies to potentially be one of the most flown over states for supersonic aircraft due to its proximity to New York City, Boston, and Philadelphia, for example. We also learned that the storage size was going to be an issue. We had a large storage size for the approximately 1 million carpets we generated just for this subset. In order to determine the importance of our input factors, we completed a decision tree analysis using a bootstrap forest. And our input factors were the heading, the lat-long, season, date, time, and ground elevation. And our quantifiers are the exposure region size, which we'll call carpet width here, and our loudness under track and the range of the loudness. So for a decision tree, you start out with all the data. Each one of these dots represents one carpet width, one realization of our propagation simulation. And the decision tree splits on your input factors. So here's what happens when you split on the heading west versus north, south, and east. So for west headings, you typically get a lower carpet width than the other headings, and that's because of the prevailing winds. When you have a headwind, it turns out the carpet is narrower. And typically, the U.S. has a west-east prevailing wind. Then the next decision tree splits on the seasons for this case, or again on the headings, and you see the east is typically the largest heading, but you go through this process, and each decision tree tries to split and predict the carpet width better for each split. The bootstrap forest analysis takes a bunch of these decision trees, and it allows us to rank the contributions of each predictor. And so in this case, again, the heading is the most important factor, and then compared to the other factors of interest, they're much lower. The ranking is much lower. The bootstrap forest then allowed us to decide our temporal resolution. We are showing here our fine versus coarse spatial resolution, and our predictor ranks for the under-track loudness, the range of loudness, and the carpet width. And what we noticed was that time of day was a very unimportant predictor, and that allowed us to reduce the size of our simulation study from 4 atmospheric profiles per day down to 1. And a clue for which spatial resolution to do was that the importance of the predictors, the ranking, was pretty much equivalent between the fine and coarse spatial resolutions. And next I'm going to tease one of our visualizations. It's kind of busy, but here I'm going to show an example of the types of data that we can share, and it'll also inform what spatial resolution we chose. So the grid of charts here shows the carpet width mean. The mean is the color of the dots in each of these panels, and the standard deviation is the size of the dot, and the standard deviation range is shown here on the right. The grid of charts, we have our seasons across the columns and then our aircraft headings across the rows. And if you just look at any of these plots, you can see that the mean and standard deviations are smoothly varying between each of the points. And that led us to choose the coarse spatial resolution because we believe we can interpolate in between those points due to the smoothly varying properties that they have. So here's our final design. We looked at 134 locations across the U.S., each of them separated by about 200 kilometers. 5 years of atmospheric data at each location, 1 time per day, 4 aircraft headings. And we resulted in over 1 million sonic boom exposure regions, each with, because each exposure region can have multiple waveforms, we have over 18 million waveforms. And we computed a follow-on analysis using multiple linear regression models in order to give us a finer spatial resolution than this. I teased some of the visualization results already, but I'll move into the results and other visualizations we chose. So the first one are violin plots. What's shown here is the loudness across the sonic boom carpet for our simulation study. Each of the violins is at a 2 statute mile or 3.2 kilometer location, so we computed the loudness of the booms in each of those positions. And the violins show the peak normalized probability density function of the loudness at each of those stations. The dotted line shows the median value in each of the violins, and then the solid black line here shows the loudness that's predicted in a standard atmosphere. And you can see that for the majority of the violins, the loudness is lower than the standard atmosphere when you use a realistic atmosphere, which is encouraging. And it also points out another limitation of using a standard atmosphere for design, in that you can get sonic booms that are much further off track than just for the standard atmosphere due to the temperature and the winds that occur across the country. We can also use violin plots to show the effect of climate. So the Department of Energy has, the Building America, put out the climate zones in the U.S. I think there's 7 in the contiguous U.S. here. And that's what's shown for each of the columns. We're showing the loudness again under track, but we can also split on the season. So we have each violin showing the peak normalized PDF of the under track loudness for different seasons and different climate zones. And there's different groups of similar seasonal results. The cold, of course, looks quite similar to the very cold, as well as the marine. And then we have another grouping of the hot dry and the hot humid. And finally, we have a grouping of the mixed dry and the mixed humid. So there's essentially, I guess, 3 groupings of similar climate zone results across the U.S. in terms of the X-59 loudness. Repeating our visualization technique for their map plots, we can show the mean loudness at each of our 134 locations as the dot color, and the standard deviation of the loudness as the dot size, and that allows you to have good visibility of 2 quantities across the country. You can see that typically the loudest sonic booms are expected from the X-59 over the northwest here, where it's more mountainous, and latitude also seems to have an impact. And then we have quiet booms in the southern U.S. that are more variable. There's so much data, right? So we can split on lots of things. Again, we're splitting here on the seasons and the headings. And plots like this allow you to do some flight planning, I guess. You can decide when you may want to fly based on the loudness you want to achieve, and you can decide how you may want to fly in order to achieve that loudness. So for the west heading, it looks a little bit more variable than the east heading. You can tell that by the dot size for the fall, for example. And maybe you wanted to get a little bit louder booms in order to have better resolution in your dose response data. So maybe you would fly east in the spring to get a little bit louder booms. I also briefly mentioned that we made a multiple linear regression model set. So this allows us to plot or estimate loudness where we didn't actually have our simulation points. But because it's so fine resolution, it's hard to see it if you have individual dots, so we only show the mean value. We leave out the standard deviation. And again, this shows our loud booms are over in this northwest portion of the U.S., and perhaps the winter is a little bit more loud on average than the fall or other seasons. In summary, the X-59 will be flying over communities in the U.S. starting in 2024 to collect community noise data. And we conducted a large-scale simulation study to assess impact of climate, heading, season, time of day, and location on the loudness, its variability, and the exposure region size. We used fast flexible filling design to decide the locations and a bootstrap forest of decision trees to help us decide our temporal resolution. We had millions of sonic boom waveforms and carpets, and we also made multiple linear regression multiple linear regression models to estimate loudness where we didn't have our simulation points. The simulated data will be used to aid in our community test planning. It'll be used to help decide when, where, and how to fly. And it also aids in the claim of national representativeness because the loudness, the X-59 is able to stay quiet regardless of where you are in the country. And with that, thank you. Thank you so much. Take your questions.
So again, if anyone has questions, please feel free to use the mic. I might repeat the questions that come off the Zoom channel. So we'll open it up to the audience.
Jason Schloop, IDA. Really interesting talk on how to reduce the loudness of the sonic boom. So when you were choosing your test points geographically, was it just based on trying to space them fairly equally apart, or did you take terrain? Like, I'm from Kansas. The western half of the state is basically flat about anywhere you are, and you've got 2 test points there. So would it be worth trying to pack more into a variable state like Colorado, where you've got Rockies all the way down to the foothills, and maybe not as much in Kansas, Oklahoma, and Nebraska, where the geography is fairly similar?
Yeah, that's a good question. I think if I were to do this again, I would try to take better account of the ground elevation and have a higher density of points in each of the climate zones as well, because some of the climate zones are small too, so we'd have fewer observations in those types of violin plots. It's a good question. Thank you.
So Will, one of the things that really stood out to me, not just the technical prowess that was used for creating these metrics, was also the data visualization that you had inherent in all of this. Was there a particular statistics package you were using to produce these violin diagrams, or was it something homegrown within your team?
I think most of these came out of JUMP. The top right's just a MATLAB violin plot that you can get on the MathWorks Exchange, I think. But in general, it was based on JUMP visualizations.
Yeah, thank you.
Shout out to Sarah for making most of them.